Welcome to the first episode of our AI Foundation series. Today, we're starting with the preliminaries and fundamental building block of AI, nerve cell, neuron. Think of neurons like the atoms in physics or the cells in biology. They're the basic units that form the foundation of much more complex systems. While modern AI has grown incredibly sophisticated, understanding these core components is key to grasping how everything fits together. In this series, we'll take a bottom-up approach, starting simple and building up, so you can develop a rock-solid understanding of AI one concept at a time. For centuries, we've known that the nervous system is the foundation of human cognition. At its core are neurons, simple yet remarkable cells that process and transmit information. Individually, a neuron's function seems straightforward, but when billions interconnect, something extraordinary happens. They give rise to creativity, scientific discovery, and perhaps even consciousness itself. How does such complexity emerge from simplicity? This question isn't just about biology, it's also the inspiration behind artificial neural networks in AI. By studying how neurons work, we can begin to understand the principles that power modern AI systems. To better understand the foundation of modern AI systems, it's helpful to look at what they're inspired by. The basic unit of the nervous system, the nerve cell, or neuron. A single nerve cell is one of many interconnected units that together form the nervous system. In a healthy and typical case, a nerve cell receives a stimulus, transmits it to its central body, the nucleus, processes it, and then produces a response. While this might sound like a straightforward system, as we might think of in engineering, nerve cells exhibit some fascinating and unique properties. First, all activity in a nerve cell happens through electrochemical signals. As we'll explore later, this is a critical aspect when it comes to modeling or even physically implementing systems inspired by neurons. Second, and perhaps more interesting, research in neurophysiology has shown that nerve cells operate based on what's called an all-or-none principle. This means a neuron either activates fully or not at all. If the incoming signal doesn't exceed a certain threshold, the neuron remains silent. But once the threshold is crossed, it fires at full strength, not halfway, not a little, but with its maximum possible response. The third important property emerges when we consider how neurons behave collectively, especially when tightly packed together in the brain. To simplify this idea, imagine lining up a set of neurons in a single row, one after the other, forming a basic chain. In this configuration, the system can only output one of two states, active or inactive, similar to a single neuron. This limited setup is not enough to carry out the complex tasks we associate with intelligent systems. Therefore, to generate more sophisticated responses, the kind we expect from neural networks in AI, we need diverse patterns of interconnection among neurons. This includes different connection paths, multiple layers, and varied directions for signal flow. We'll explore how all of this comes together in future episodes. To understand the potential of interconnected neurons, let's start with a single one. Assuming an all-or-none response, a neuron is stimulated by many inputs and delivers binary decisions. Yes or no, move or stop, heads or tails, 1 or 0. Technically, all or none means a neuron produces just one output when activated, always at full strength. Therefore, a neuron is either activated or silent. So, binary states here represent either full strength output or activated, example, yes, or no output at all, or silent, example, no. Why emphasize the full strength? This subtle detail hints at a neuron's internal parameters, which become crucial when multiple neurons interact. But first, let's examine the no output case. It reveals another key property. The threshold principle. A neuron fires only if its stimulus exceeds an internal threshold. Otherwise, it stays silent. From the output side, you can't distinguish between no stimulus at all, or a stimulus below threshold. Back to full strength. Once activated, a neuron delivers its output at the highest possible strength, a unique intrinsic property of each neuron. Again, observing the output only tells us the input crossed the threshold, not by how much. Why does this matter? From a modeling perspective, a neuron's output can jump dramatically from 0 to full strength based on a tiny threshold adjustment. This means the same input can trigger different responses if the threshold changes. Different neurons may react uniquely to identical inputs due to varying thresholds. Since one neuron's output often becomes another's input, these two parameters, threshold and full-strength output, create a feedback loop. Tweaking them can produce vastly different network behaviors. This is the power of a neural network. In summary, a single neuron operates with two key parameters: NAT, or neuron activation threshold, which determines whether the neuron fires for a given input, and NMO, or neuron maximum output, which is the fixed full-strength signal it produces if activated. From the output perspective, you only ever see NMO or nothing, no in between. While this seems simple, its implications are profound. In fact, this all-or-none behavior is what makes neural networks such powerful universal computing tools. In this animation, the white bar in NAT represents the neuron's threshold value. The rising yellow bar shows the input signal strength. As we observe, the neuron only activates if the input exceeds the threshold. Once triggered, the neuron produces its maximum output, NMO, at full strength. This demonstrates a fundamental principle. We only ever see NMO at full power or nothing at all. There are no partial outputs. It's all or nothing. Before we wrap up, let's explore how this all-or-nothing behavior enables universal computation. Observe how the neuron's output changes over time. For any given input signal and NAT-NMO configuration, the output is always either 0 or a full pulse. This binary response is deceptively simple, yet it holds the key. As we'll demonstrate in future episodes, this fundamental property is what allows neural networks to compute anything that's computable. To accurately model a neuron, we must account for both NAT, or neuron activation threshold, and NMO, or neuron maximum output. These components are independent yet interrelated, exhibiting a two-stage mechanism, which suggests our modeling approach should also follow a two-step process. Let's simplify the problem by examining it from the neuron's output perspective. Stage 1, modeling NMO. NMO can be represented by a single numerical value. This value may differ across neurons. Each neuron has its own NMO. Over time, due to aging or environmental changes. However, at the moment of operation, NMO is a fixed number. When combined with NAT's triggering mechanism, where an input generates an output, this behavior can be neatly captured by a mathematical function. Here's how. The input to the function is the NAT process. The function itself is designed so that if NAT exceeds the threshold, it produces a non-zero output. Stage 2, handling multiple inputs. A single neuron rarely processes just one input. In fact, a neural network with only one neuron, or a linear chain of neurons, cannot generate complex outputs. Therefore, we must account for multiple inputs in our model. This means extending our single-valued function, representing NMO, to combine multiple NAT inputs into a single value, and feed that value into the activation function to complete the modeling chain. But before diving deeper into this, let's first ground our understanding with a real-world example. Imagine deciding whether to attend a sports game happening nearby this weekend. In a single neuron model, this decision has multiple inputs, objective factors, and a single binary output, attend or not attend. Input examples: distance to home, possible values, nearby, in the town, downtown, neighboring state, other coast. Stakes of the game, possible values, local league match, Champions League final, World Cup final. Critically, these inputs are objective observables, not subjective opinions, a key distinction for future mathematical modeling. Assume we scale each input from 1, lowest interest, to 5, highest interest. For example, input 1, distance, 4. The venue is somewhat far. Input 2, stakes, 3. The game is a Champions League final. Here's where the real power of neural networks shines: personal bias and change over time. Another person in the same house might evaluate the inputs differently. As we age, our priorities shift. Perhaps distance matters less, but social engagement matters more. Thus, beyond objective inputs, we need a flexible mechanism to account for subjective evaluation and temporal changes in neuron behavior. Now, back to modeling. To generate a single output, we must condense multiple inputs into one value. How? Possible approaches could be taking the maximum, only the highest input matters, ignores others, or median selection, which requires sorting but adds computational complexity. Neither is ideal. Sorting introduces delays, and maximum or median discard valuable information. This is where the weighted sum approach comes into play. Each and every input is weighted by a corresponding coefficient, and all the weighted inputs are summed together to obtain a single value to be passed on to the function which will generate the neuron's output. This way, a neuron combines inputs proportionally based on importance, weights, and a computationally efficient process is adopted. No sorting needed, and utmost flexibility, weights can adapt over time or between neurons, is achieved in modeling a neuron. This leads to the next big question. How do we determine the optimal weights? Optimal weights, the recipe for combining multiple inputs into a single value, are fundamental to AI. They influence the number of parameters in a network, the size and structure of the model, how neurons and the entire network behave, and training efficiency and learning dynamics. But what does optimal really mean? Optimality implies there's a mathematical criterion, a set of conditions that define the best possible solution. To reach or even approximate the solution, we rely on mathematical techniques that guide us there reliably. This is where the weighted sum approach gets into the game. Not only does it simplify input aggregation, but it also opens the door to powerful optimization methods. For our curious audience, the key lies in linear algebra. Stay tuned for deeper dives in future episodes. Let's break down our model to understand two key concepts. 1, how weighted averaging works, and 2, how an activation function generates the neuron's output. Imagine we have just one input neuron with a single input value, non-zero, random, and a corresponding coefficient, weight. Inside the processing block, our neuron's computation has 3 components: a summation unit, combining weighted inputs, a bias term, B, an additional constant added to the sum, and a function or mapping unit, applying the activation function. Recall our 2 key internal parameters: NMO, neuron maximum output, represented by the function block, and NAT, neuron activation threshold, captured by the summation and bias components. The bias term serves a crucial purpose. It adjusts the activation threshold, NAT, regardless of input, acts as a constant offset in the summation, and physically corresponds to modifying when the neuron fires. By changing the bias value, we're effectively tuning the neuron's sensitivity, making it fire at higher or lower input thresholds. Let's walk through a concrete example of how our neuron processes information. Example 1. Basic calculation. Input value, x, 1.33. Weight, 2. Bias, 1. Step 1. Weighted sum calculation. 1.33 times 2 plus 1 equals 3.66. Step 2. Activation function. This 3.66 value now enters our activation function. We have several options for this function, including linear, ReLU, unit step, logistic, or sigmoid. After selecting and applying one of these functions, we feed 3.66 into the function, read the output, assign this as the neuron's final output. Example 2, different parameters. Let's examine another case with different values. Input, 0.5, weight, 0.74, bias, 0.25. Calculation, 0.5 times 0.74 plus 0.25 equals 0.62. When 0.62 passes through the same activation function, it might produce an output of, for example, 0.55, demonstrating how different inputs lead to different outputs through the same processing pipeline. In this episode, we've examined the fundamental biological unit of neural networks, the neuron, simplified its complex structure through careful assumptions, developed an accurate mathematical representation. Our model mirrors biology with input units, like dendrites, processing modules, like cell body functions, and output terminals, like axons. Just as biological neurons, we've designed our model to handle multiple inputs and produce a single output, incorporated crucial flexibility through weighted averaging and activation functions. Coming next, we'll continue building your AI foundation by exploring other essential neural network components. Stay tuned for deeper insights, one frame at a time.